Okay guys, welcome back. Today we're gonna go over the lab. Expect from you already have this screen. The first thing, once you log into the virtual machine launching the CS458 Lab, so here, when you click terminal, here you can write whatever you want, okay? Let's first, I'm gonna say make directory, create directory in order to work in this one, okay? Let's say class, or let's say lab 2, lab 02, just to put all my folders that's associated with this lab in one place. Then change directory to the lab 2, and you can move there, okay? You can say ls, if you have anything you stored there, you can list all things that's stored in this lab. We study in the secret key encryption, we talk about substitution cipher. So here, I'm not gonna explain what's the substitution cipher, but we said we do have two different types of substitution cipher in general. One is called monoalphabetic, the second the polyalphabetic. So the mono one that the one that we're gonna study in the lab that you try to test is similar to the class activity that you did before. Okay, but here I'm going to encourage you to use the tools that installed in this machine, okay, in this virtual machine. Okay, monoalphabetic here, we're going to use what is called the fixed substitution over the entire message. For example, if the letter A is substitute mapped to the X, this means all the time, once I reach or find out, for example, the plain text, a letter A, I'm going to map this one to the X. Okay, when you reverse the operation, when you decryption, you will also find the letter X, it's going to be remapping into A. Okay, the polyalphabetic is not going to cover it here in the lab, which you do have a number of substitutions at a different position in the message. Okay, sometimes A is going to be mapped to the X, sometimes letter A, the plain text is going to map to whatever. Okay, so in the monoalphabetic, the substitution cipher, I want from you to perform encryption and decryption. I give you the file. So how can you perform encryption and decryption here? I'm going to introduce you to commands that you can use in Linux, okay? The first one, translation or translate, TR command. TR command that allow you to what? In translating or deleting characters. Remember when you said what? You have a plain text and actually you have a ciphertext. Then you need to correct this ciphertext, decipher it, okay, use the frequency and else. Actually, most of the time you're going to do what? You figure out, for example, it looks like the letter X in the ciphertext, it looks like this is the letter E. Once you find E in the ciphertext, you need to translate it or move it, change or map it to another letter, let's say E, okay? You can use this one using translate. You don't need to open the text, the ciphertext file, then you do this one manually. We have some commands. Let's have an example, okay? If we try to create a file, okay? In the file, I'm going to say, for example, you can use an echo command, or you can use touch, then after that do the echo. Or you can use whatever editor you have, VI or Nano or whatever. You have the options here, okay? Sometimes we prefer use echo, sometimes we add the command, the option -n in order to make sure that when you create a message that contains only 6 bytes or 6 characters, I don't want the system to add the /n at the end. It's going to be 1 extra byte. So I need only the exact character is going to be part of the message. So in this case, I'm going to do echo -n, okay, or -n. So forget this one and say the message that I want to write, for example, let's say this is the first time, okay, working, let's say, whatever, with C labs, for example. This is my message, okay? Then after that, I'm done here. Then you enter here. So the message, okay, don't care about TAH or TEH, okay? What happened? I did this echo. Did I store this one somewhere? No. So I want to store this one in one file. So my chance now to fix it, okay? So this is the message. Then here you can specify, for example, where you want to store your message. You can say, for example, but this one, this is a greater than, this means it looks like, but whatever you have is stored on this file. I'm gonna call this file the plain.txt, okay? Then we store this one, the data is going to be there. How can you display that? Let's see, ls, it's going to show you that the plain text is created there. Then after that, you can say cat, the plain here, and you can see, show me the content of the message. So this is the plain text. Then assume that you're going to perform encryption. Remember, it's substitution cipher, okay? The simple way to do that, if you have a plain text, you wanted to perform encryption, it looks like you need to tell me a specific order, for example. For the letter A, it's going to be translated mapping to whatever you want. Assume that we wanted to do the following transaction, or they say substitution cipher. A is going to be translated or mapping to the J. B is going to be translated or mapping to the L. C is going to be to the H, okay? Something like this. How can you do this command? So I'm a lazy guy. I'm going to copy the command. It's already there, just save your time. Then this is my command here. Just show you here. Translate, space. This is from A to Z, okay? There's the lowercase, all of them lowercase. space into what? Into the following. So A is going to be to J, B is going to be to L, C is going to be to H, and etc. Okay, and the input is going to be the plain text, and here it said the output. You see the greatest sign then here will be to the output here. Then when you enter here, translate from A to Z into this, from less than the plain text into the ciphertext. So the ciphertext is going to be contains this information. In order to check what the content of the ciphertext, you can say cipher and you print out. This is the outcome. Do you see what happened? I managed to do substitution cipher. So how can you decrypt using the simple thing here? I'm going to use the TR, the same command. I'm going to use the same command. The only difference, honey, you need to specify. You transfer from what? From J to Q with my substitution, so into A to Z. So that means that J is going to be translated to the A, L is going to be mapped translated to the B, and etc. From where? From the ciphertext to, you can specify two results, or if you don't specify the output, the system is going to say, okay, no problem. If you want to display this one, if you don't tell me, I'm going to put this one here. Show you this result here. In the class or the lab, I expect from you how can you use the frequency analysis in order to breaking the monoalphabetic ciphertext or substitution ciphertext. So you see that you're going to perform the frequency analysis. I give you, there's a few links. You can use them. You didn't need to count by your hand, for example, what the occurrence of every single letters. You can use some online tools. You just copy the ciphertext and it's going to show you, for example, the letter A is occurs 100 times, the letter B is 16 times, etc. Use them, okay? Then after that, you need to figure out what? You need to find what's the common letter that you have. Then after that, what the common two letters combination, what the common three letters combinations, and etc. Assume that you want to, for example, perform some operation of the text that we have. Okay? Let's assume that you want to see or highlight or let's say search text or file for the occurrence of the string character that match specific pattern. And I guess all of you work with Unix before, or Linux system in general. So you know the gap, okay? With the global regular expression print, with the command getting used in order to help me like filter search, okay? Filter search is the file for the particular specific pattern. Let's have an example here. Assume that I want to say, for example, A, okay? I'm looking for A in the ciphertext. It is going to highlight as A. So just show you, for example, if you have a ciphertext that we have, you want to see A how many times occurs, where is the place it's going to be appears, or you search for the specific pattern. You're going to see, give you some hint, okay, what's going on. What if you try, for example, I want just to print out the matching non-empty part, only the matching values of the A. So if you modify your graph here, you can use some keys. By the way, if you want to get the manual about whatever command here, you said grab here, grab and give the manual, is going to give you more details about what's going on. What kind of, let's say, matching your controls or options you can use in order to help you in order to find out, achieve your goal, okay? I don't want from you to, memorize anything, but just to practice, to play around. And actually, during the lab, maybe you need to perform these commands. So just I introduce you, make sure that you are familiar with this kind of command. Okay? So if I said, for example, grab minus O, that means in this case only matching value. I don't want to give me everything. Don't highlight the pattern that I'm looking for, but just show it to me. Okay? So A, and from the ciphertext here. Get me here? Just show you the A's here. Okay. We can add another command, which is called unique, which Linux command in general, allow me in order to compute the number of accounts, for example. Allow me to report and you say, or filtering repeated lines and files in general, okay? It can remove duplicates, for example, count of the accounts of a specific pattern, and etc. So in this case, I'm gonna combine both of them. I'm gonna do A, okay? Try to count the number of accounts, and also I want to ignore the case when comparing, regardless it's gonna be uppercase or lowercase. This is going to produce A's. Then I want from this one, it's going to, for every single entity, A or B or C or whatever, how many times this one occurs in the system. So here you have a pipeline. Here I'm going to say here that the outcome of the first part, the operation, perform the unique. And the unique, I'm going to use two keys here, I/O. The I, that means ignore the letter case, upper or lower case, when you match or compare. And also I want to count the number of occurrences that you found the output with A's here. Oh, C, sorry. C is the count, of course, not O. Okay. And this here is going to be C. A is of course 6 times. So it's going to help you just to try to get some information, useful information about the system. So assume that you figure out or find out, I want map A to the C and B into to the D, for example. Okay, so how can you do that? You can do this one using that command. Okay, I clear here. Assume the translate, for example, I want from A and B. It's gonna be mapping into the say C and D. So you have a choice. Either you can specify A is gonna be to the C, B to the D, E or whatever to the F or whatever. Okay. After that, you say for the ciphertext. Okay, I can put this one as an output text if you want. Put this one in the output. In my case, just I want to see whether I have something or not, whether can be do this one or not. You see that if you let me here cat this is the ciphertext just to make sure that what happened. The ciphertext this original one, and this is after you perform this operation. Remember, you can store the information or result in output file or any file. I didn't include that. I want to do this one because I want to show you the result here. So you see that for the A, every time you find A, it's going to be mapping to the C. Okay. Every time you find, for example, B, it's going to be mapping to the D here. If we have D, I don't think so. We have B here. Just an example. So all the A is going to be mapping to the C. So you managed to perform this operation. So this one, using the translation or translate TR command, is allow you in order to apply whatever information that you received or you did use or derive after perform frequency analysis. Either one letter mapping or 2 letters, you need to move them or convert. Once you find AB, put this one CD, for example, or that. THE, for example, you find something AWE is going to be THE, for example. Then you're going to perform the operation. So letter by letter, you can perform that mapping. The other thing that we're going to perform, we're going to see in the lab, which was called the Advanced Encryption Standard. We have a DIS, Digital Encryption Standard. Mainly we're going to work with the advanced, with AS in this lab, okay? But you can perform the same operation that you want, and you can perform encryption, decryption, etc. Just to remind you, what's the Advanced Encryption Standard? What's the size of block size? It's the block size. What's the block size for the AS? 128 bits, okay? Then, how many keys do we have? We have 3 different keys, yeah? 128, 192, and 256 bits, okay? Good. We do have many encryption modes. We talk about this one, since it's a block cipher, yeah? And just to remind you, what the encryption mode is like a mode of operations refers to what? To many ways or different ways to make the input of an encrypted algorithm different. This is in general. And you try to encrypt the message, the size of the message greater than the size of the block cipher. So we need to find out a way, how can you perform the encryption in this case? Whether you do this one using the electronic codebook or use a cyber blockchain or counter, and you're going to see that we have a different encryption mode. You can use them. Okay, in the lab, I'm going to introduce a different one, so you have to perform some, go over this one, make sure that you understand every single encryption mode, how it works, how the message, what do you need, whether you need initialization vector or not, what the message is going to be encrypted, or maybe you're going to use whatever the key just to generate cryptographic bit in order to perform the encryption. So the structure is very important. The encryption, decryption process is very important. You need to be familiar with this one. How can you perform that? We are lucky that we're going to use, in the lab is already used what's called the OpenSSL, which is what? It's a C library that implements the main cryptographic operations. So it implements the following cryptographic operations: symmetric encryption scheme, public key encryption scheme, digital signature, hash function, and so on. All of them is already implemented. So what we're going to do here, we're going to use this library in order to try to perform encryption, decryption, and etc. Okay? So first, let me double check whether the OpenSSL is already installed in my machine or not. In order to check that, you can use just, let me clear this one, okay? So you can use what's called OpenSSL version. Okay, so if we show you the name of the command or the tool that we have and the version, so this is showing me that the OpenSSL is installed. Good. How can you use them? Let's have something. Let's have some commands. First of all, I want to see, for example, what kind of command I can use with the OpenSSL. Of course, I don't want to say let's use without understand what's going on. So this tool or this command or this library, if you said OpenSSL space list dash standard dash commands, is going to show you all the commands that we're going to use. Okay. The most important thing that mainly we're going to use today and this lab, during these labs, I'm going to use the encryption here. So we do have what the command can be associated with the OpenSSL. If you said encryption, now you're going to start using the encryption. Okay, then let me ask or go over, for example, what kind of encryption algorithm already implemented here. By the way, for this encrypt, or this tool, allow me to perform encryption, decryption at the same time. It's not decryption, it's encryption and decryption using the secret key algorithms. Okay? So it's possible to generate using a password or direct secret key stored in the file. It depends on you, whatever kind of operation. I'm going to go over multiple operations. How can we use this encrypt, okay, to perform encryption, decryption using the symmetric encryption scheme, which is what we're going to use in the lab here too. Okay, then I'm going to show you how, for example, use the key, whether the key is going to be given in the command, or maybe you can use this one in the file, or maybe have a secret key best used as a key. You have many ways. Okay, you're gonna see if you take a look here, you have, for example, RSA with the one gonna generate the public key, private key. I'm planning this time to work with the public key encryption scheme too. If you take a look down here, you see that you have a salt. We have X509. Later we're gonna talk about the certificate. How can you generate it? Maybe we can use this one. Hash function, we can use the hash function with check and etc. All of them are there. Okay, so now down. Okay, we're gonna use encryption. So give me what kind of ciphers are available here. What kind of, let's say, secret key algorithms are available here. Okay. So if you type this, OpenSSL space list cipher command and enter. Here you're gonna show you AES, for example, here. So if you wanted to perform encryption using the AES, okay, then the key or the size of the key that you're going to use is 128, and you want to use the encryption mode CPC, electronic code book, for example, and the size of key 256. So you have to use this as an option when you say, for example, OpenSSL encryption, and the encryption scheme is going to be used AES 256 ECB. So this one is going to specify what kind of encryption scheme you're going to use. Okay, the size of the key with the second column, and what kind of the encryption mode or operation mode you're going to use in order to perform this encryption scheme. So all of them are there. If you take a look at the lab, you see that we have to use something like the AES, the size of the key, then after that, the encryption mode. You have to specify what kind of encryption mode. If you wanted to perform digital encryption standards, this is the way to how to use digital encryption standards. Okay, this is, for example, triple this. And etc. All of them are there. Okay, if you have used RC, for example, 4, etc., I think we're going to cover this one later. So some of them, okay. So again, we cannot go over all of them. So mainly in this lab, we're going to work with AES, and mainly the key is going to be 128. But you have a choice to use whatever you want. Okay, okay. So here, either you're going to perform encryption, decryption, you're going to use the same algorithm. Good. Now we know what's going on. We know what the size of the key and etc. So let's perform like. Do some tests, okay? I'm going to create a text, okay? And this text, plain text, I'm going to perform encryption, decryption, and see how can we use that, okay? And the way that you create a text is many things. You can use a touch, create a file, empty file, then after that, put the echo and put the data on the file. Oh, let's do this one, echo. Let me try to use nice, let's say, plain text. Let's try to express your feeling toward this class. I hate my instructor. You agree with me, definitely. Okay, this is my plain text. I can't change to I hate my students. Okay, so anyway, we create this one. And we have this plain text one. If you have ls, it's there. If you do cat, just make sure the file, just make sure the file has this information. Plain, we do have 2 of them, then plain 1 text, so I hate my instructor. So this is the plain text. I want to encrypt it. What do you want? Let's say, assume that you want to encrypt this one using the AES algorithm, using CPC mode with a chain block mode. The key is 128. How can you perform that? So you can do this one. This is one way to do that. You're going to say OpenSSL first. Then after that, I'm going to perform and use encryption, symmetric encryption scheme. Okay, encryption, decryption. Okay, what are you going to use? I'm going to use AES. Remember, I got this one from where? From the list of cipher commands. Okay, then the size of the key 128, and the, let's say, the operation mode, or let's say encryption mode is CPC. Then specify what's the input file. The data, the input is gonna be the plain 1.txt. Okay, good. What's the output? I want to put this one minus out into, let's say, cipher 1. And usually we put this one as a binary because later we're gonna work with the hexadecimal and etc. Okay, text binary is fine. Okay, here I didn't specify the key. You can specify the key. I'll give you two different options. Okay, one way I'm not gonna specify the key, but the system gonna ask you to tell me what's the password or key you're gonna use. When I enter here, I'm gonna say, okay, give me the encryption password. The system gonna use this one in order to generate a key using like a password. When you type, by the way, you cannot see it here, okay? Assume that I'm gonna use the password, gonna be safe, S-A-F-E, okay? When you enter the system, say, please verify this one, S-A-F-E, again, and now it's encrypted, okay? Let me have, let's say, ls, you see that we have ciphertext one. Let's see what the text here, how can you see the content of this one? Well, it's binary, do you see? You cannot read this one clearly. So we do have another way. Once you have encryption using the AS or whatever encryption scheme, is not, substitution cipher, you text to text. Here we're gonna have some characters that we cannot see them, okay? Yeah, by the way, when you use the save, it's too small. It's not good to use this one because it's too short. It's not unsecure, but just I use this one as an example. Anyway, when you try to get the value here, you see what the content, you see most of the data is not clear. You cannot read them once the file is going to be encrypted. So let me clear, just to go up here and see how can you perform this. In order to see the content of the file, the ciphertext, the file that contains the encrypted data, you can use XXD, which what's called, the command line hexa viewing tool. Okay, allow me to see this one in hexadecimal, which is the one I'm going to use a lot during this lab. So XXD, then after that you show me the cipher one, and this is the way you see that. This is hexadecimal. You can see here. Okay. What's the size of the message of the ciphertext is going to be here? What do you think? It's supposed to 128, yeah? Yeah, this is because it's your AAS here. Yeah? Unless the block size is going to be larger. Yeah? But in this case, what you're going to do, I can't get, let's see, I think I can use ls minus L to get information about this one. This will be cipher 1, binary, give me the size here. It's give me 48. Why? 48 bytes multiplied by 8 equal to what? We are going to go over this one because what's going to happen here, the system is going to use a padding here, okay? And this is ciphertext, okay? Because you need to encrypt the message. So the system is going to use a padding here because the size of the message is greater than the size, the plain text. I will go over this one later. But yeah, I'm with you, Adam. We say I have the plain text 128 bits and it's going to be encrypted to the 128 bits. But the input is not 128 bits, it's larger. So in this case, the system is going to do what? It's going to maybe use the ciphertext. Remember, it's going to combine all the ciphertext that we have in one of them. Okay, because it's like whatever the different operation mode to perform the operation. I'm going to go over this one later to show you what's the difference here. How can you get rid of the padding? How can you show the text with the padding and without the padding? Okay, so how can you decrypt that? In order to decrypt that, I'm going to show you the simple thing here. Let me go up to my examples and say use a save. And now if you try to encrypt the message here, what I'm going to do here, I'm going to use different way to perform that. I'm going to say encrypt, the same thing, AS, the same encryption scheme that you use, it's the same structure, the algorithm, the size of the key, the operation mode that we use, and here I'm going to use -D. -D, that means decrypt. In order to emphasize, I'm going to perform decryption here. The input is going to be the cipher one, and dash the password. You can give me what's the value of the password you perform. This is one way to perform that, okay? You see that now we managed to have the original message. You can, of course, store this one minus out in another file, but I want just to do this one in this easy way. So let me show you, for example, what we're going to do in the lab actually. What kind of command you're going to use. I'm going to modify this one a little bit, okay, to use the exact command that we're going to perform the lab. So in the lab, for example, you're going to use OpenSSL command, okay, and assume that you're going to encrypt the plain text and store it in the ciphertext. And I'm going to call the ciphertext 128 ECB, for example. I'm going to use electronic codebook and see how can you perform or add the key here. This is how it looks like. OpenSSL space encrypt, then whatever encryption scheme you're going to use, 128 ECB with electronic codebook. Then after that, -E, that means I'm going to perform encryption. Decryption, that means minus D. Then after that, dash N, actually use dash is better, not minus. N, the file input is going to be plain text 1. And dash output, then we want to put the results, the output in the file is called CS458 ACB. Okay? Then the plain text, let's say the key here, the difference here, the key. The key, I'm going to write my key here. This is the way that you're going to perform here. Remember, the key is input for the 128 must be 128 bits. In order to find how many bytes you need or how many characters you need to divide this one by 8. Yeah, then multiply by 2 is going to tell you how many characters you have to use. We're going to use a simple key here. As you see, 0001, 12, 22, 33, something like this. In order to make sure that we have the key, and the size of the key must be 128 bits. Okay? Do you need to add initialization vector here? No, because I know how the electronic code book works, and I know this one doesn't require. Okay? So let me perform that. Hopefully it works. And that means the ls here is going to show me the result of the ciphertext that I got here. Okay? In order to decrypt this one, okay? Oh, let me see. Yeah. Again, the key here is 16 bytes, which is going to give me 128 bits. You can use any random number. And this is the way minus K or dash K to specify the key position, which is exactly what we're doing in the lab. So in order to decrypt the operation, I'm going to do the same operation, but the only thing I need to change here, if we write copy and paste here, just to save the time, the same OpenSSL, encryption, whatever the same encryption scheme, here minus D and dash D. I don't know why I'm keeping saying minus, it's not. Okay, then dash input. What's the input? The ciphertext. Do you need to put the output? You can specify the output. This is one of the output. Do here dash out space and write the output file that you want. Here I want to save the time. Instead to store this one in the file. Then after that, I want to see the content of the file. You need to perform the cat. I want just to display the result here. And you have to use the same key. Otherwise, you are not going to get the result. You expect to see what? You hit your instruct, which I mean the outcome. So we perform encryption, decryption using ECB. You're going to see in the lab, you're going to perform this one using different encryption scheme, different operation mode or encryption mode. So you need just to create different messages, plain text here, you're going to perform that. Okay, you're going to have, for example, the cipher block chaining. We talked about this one before. Here in this case, you have to use initialization vector as the input, if you remember that. Yeah, so here we need to input the initialization vector as the input in order to perform the operation. So I will take the same plain text, okay, let's encrypt it using the AS, the same key size, 128. Then we're going to use, for example, CBC mode with the cipher block chaining, okay? So how can you perform that? You're going to do that. The simple thing. By the way, if you forget what kind of encryption scheme you can use, how with again AES 128 and etc., just need to make sure that you go to the OpenSSL, list the cipher command. If you forget these kinds of encryption scheme that's available there, go this one. It's gonna remind you what kind of encryption scheme that we can use here, such as a key, yeah, or the option or filter. Yeah. Clear. Let me do the encryption use CBC. Then after that, we try to compare them. So I'm gonna hit the initialization vector is written as following. You see OpenSSL encryption, that's perform encryption with symmetric encryption scheme. That's the meaning here. And here the keys or the parameter is gonna be the AS 128 CBC. Okay. Dash E encryption, input the plain text file, and the out cipher is a chew.binary. Okay. Yeah, I prefer to use the binary as extension. This is the key, minus dash K. Then after that, dash IV. Put this one small. Don't put the other case, the system gonna refuse. This is the structure, must be small. When you perform this operation, what the initialization key size? It depends on what. It's gonna perform exclusive over the plain text. Yeah? So it's gonna be the size 128 bits here, because similar to the size of plain text. We use 01, 02, that's simple one, okay? Of course, in a real application, don't use something like this. Even the key, don't use the keys like this. Easy to predict, or easy to guess. When you perform the encryption, I perform the encryption here. And the second one is to decryption. I will perform the encryption, decryption, then I'm gonna work with this one. So this is the encryption, and this is the decryption here. Open the same command, the only thing here, decryption, input. The input is going to be the ciphertext, of course, and the out I will put this one in the result to the text. And the same key and the same initialization vector. Then after that, perform encryption. Okay. Then you can use what is called the cyber feedback, which another block mode. We didn't cover this one. This is different a little bit. Yeah. The cyber feedback block is you have to go over this one in the lab. But I mean, it's easy for you to understand because you have initialization vector is going to be as an input. Then use the initialization vector and perform the key as input and the initialization vector as an input instead using that as a message as an input. In order to produce what is called cryptography, a bit stream, then after that you're going to exclusive all with the plain text. It's explained in the lab. Yeah, I think in the lab you have to go to the link to read over more details about this kind of encryption. And now you are in the position that it's easy for you to see what the encryption function, what the decryption function based on the whatever operation mode that you have. Okay? So let's do this one. I will use the same one, and here I'm going to use the same plain text, and let's encrypt this one using the cyber feedback with the CFP, with different operation mode. The same thing, the only difference is put another encryption mask. Okay, different. So we have cyber 2 from the CBC operation mode, and the cyber 3 is going to be the outcome of the cyber text that after I produce or using this encryption scheme, encryption mode. In order to compare whatever you have in the data here, we're going to use ls, list, minus L in order to give you all the details of the command, all of the access right. We're going to use this one a lot, especially later when we talk about the access right. When someone acts in the computer, how the system of the Linux or Windows is going to enforce the access right. So the access right is going to be enforced as what? As a read-write, execute operation, okay, with privilege, whether you are permitted to perform this kind of operation or not, okay? Okay, so here let's say the plain text, plain one, which is the original plain text. I want just to compare the size of the plain text and they see what the size after perform different operation scheme or the encryption scheme. Then here the cyber 2 with what after perform CBC. Then after that the cyber 3 which after perform cyber feedback as operation mode. This weird. When I click enter, I saw the result in the my iPad and in my computer still learning. Now I see the result. That's strange. Anyway, so you see that you cannot see the size of the plain text is, take a look, the plain text is 22, okay? And the size of the cybertext here, after perform what you call CFP, it's going to be 22. So the cyber plain text is equal to the cybertext. But for the cyber 2 with the CBC here, it looks like we have what? The size is larger than that one. Why? Which back to your answer, Adam, when you said it's supposed to be 128, but we got this one larger. Why? Because here I have the cybertext, okay? The cybertext is going to have like a padding. It's going to be part of the result. So we can tell the system first, when you encrypt or decrypt the message, whether get rid of this padding or keep it. Okay? So we can tell, we can play around. But here the difference of the size of between the plain text and the cybertext because of due to the padding here, which is the one that we're gonna cover in the lab. You're gonna go over this one. You start playing around with the padding. So you need to create, let's say, 3 different plain texts with different size. One of them less, one of them maybe similar to the size of the plain text that you use on the encryption scheme. One of the larger, in order to see what's gonna happen here. What kind of padding? We cover this one, the padding. Yeah? Remember, sometimes the size of the plain text they try to encrypt of the block is less than the size of the block required in order to perform the encryption. So we need to add more extra bytes. Okay. If you take a look at the padding, let's say something here. Let's see, assume that we have another plain text. This is to play around here. I create -n, this means I don't, the /n is going to be part. Don't include. You remember when you create a string, the system is going to be /n as end of the string. I don't want this one. So here we have 9 bytes, that's 9 characters, then the plain text is going to have exactly 9, no more. That's why, because I said the /n. You're going to use this one when you play in the padding. Okay? Just create this one. Let's be clear. Okay? Do you want to see it? You can say cat here, the plain 3. The text, I'm looking for this, you see, because it didn't have /n, so there's no end of the line that's going to be printing the same line. Okay, good. This is clear here. I do have the plain text 3. Then what I'm gonna do here, I'm gonna encrypt it using, let's say, CBC. I want to see what's going on with the padding here. What's going on? Why this one is gonna be larger? I expect this one is gonna be the same plain text, the ciphertext, yeah? Or at most it's gonna be 128 bits with the padding. So let's encrypt this one. And I'm gonna use CBC, okay? And the encryption mode, and the result gonna be in the cipher form. Minus KIV, all of them are there. Someone has said, do I need to use initialization vector chain block code? Because we need it. Yeah, even if you add one parameter that you don't need in order to perform this operation, the system is going to be fine with that. Anyway, so when you perform that, I encrypt it. So first, let's see the ls minus -l. Just give me more details about the structure. How many bytes, who can access what, and who's the owner of this file, etc. With the cipher for that we just generated or just created. We see this one is what? Is 16. Why? 16 bytes. Why is not 16 bytes? Because of the padding. Okay? So if you take a look here, let's put this one here together next to each other. Sorry, the plane 3, not 1. Because this is the original message. Remember the plane 3, we work with the plane 3 here. So 9 characters from 1 up to 9, and here this is 16. Why? Because of the padding. Okay? We can play around, you can remove this one, we can get rid of this one. So how about if I decrypt this plain text? Do I gonna get 9 characters, 9 bytes, or it's gonna be 16? Of course, when you perform the decryption, the system gonna automatically say, remove all the padding that I put here. So what I did, I just tried to reverse this operation. Take the cipher plain text form, ciphertext that we have, decrypt it, and put the result as the plain 4, okay? Just in, hopefully plain 4 is gonna text is gonna have equal to the plain 3. The same key, the same initialization vector. Then here, let's say here plain 4. Okay, you see it's gonna be end 9. If you want to get the result plain 4, and this is gonna be 1, 2, 3, 4, 5, 6, 7, 9, 8, 9. Okay, we managed to do this one. Okay. So I think I have one example just to add to make sure that how can you remove this one, okay? How the decryption, for example, software know exactly where the padding is starting, how it's going to get rid of this one. The OpenSSL has what is called an option called no pad, okay? This option, okay, if you don't want the OpenSSL to remove the padding bytes, then you can add this one. When you perform the decryption, the system is going to say, okay, you want for me to perform the decryption? Yes. Do you want to keep the padding that I add to the original plain text to make the size of the plain text is equal to the size of the block size in order to perform the decryption? I'm going to say, yes, don't remove it. Let's see it. So in this case, if you have this command, the only thing is going to be the same one. I'm going to take the ciphertext 4, then decrypt it, and here just add, let's say, clear. Add one option here. The simple option is going to say, no pad. Please, don't remove that. I don't want you to remove that. And put the result where the plain text 4, okay? Then when you perform this operation, let's say ls-l, let's say 4, the text. It's 16. What happened? The padding is there. Do you want to see the padding here? Let's take a look. This is nice to take a look. The problem is on my keyboard, not my fingers, okay? Yeah, you have to blame the keyboard. Do you see that? If you take a look, this 1, 2, 3, 4, 5. This is the hexadecimal 5, 6, 7, 8, 9. Then, you know, what's the size of the block here that you use in encryption scheme? Must be 16 bytes. I do have 9 bytes. So in order to have 16, I need to add what? How many bytes? The size of encryption scheme, the block size of the encryption scheme that I'm using right now is 128 bits with 16 bytes. The message that I have has only 9 bytes. So in order to encrypt this one, I cannot encrypt it. I need to add padding. So how many bytes I need to add here? 7. In order to have the total, it's going to be exactly. In order to have the total what? 16. So we see that we're going to have 07, 07, 07, 07, 07, 07, 07, 7 times. Now this is a blame. Because what I've said here, I said, please don't remove them. I know. When you encrypt the message on the size of less, you're going to add that one. Okay? Add padding. When you decrypt, the system automatically going to remove this one. That's why the ciphertext is going to be larger. Okay? Because of the padding. Larger than the size of the plain text. Okay, when you try to perform, let's say, decrypt this one, the system automatically remove the padding. So I say, no, please leave them. I don't want me to remove them. So that's why you can't see them here. Okay, so you can't tell the plain text is here and the ciphertext is gonna be. Let's try to do something weird here. I have to say plain, let's say, for the text. I will just see what's gonna have here. It's gonna be showing because the system is gonna know, because here it's padding. The system has a knowledge that is not gonna be part of the result. It's not gonna display it. But if you use XXD, which is the tool is gonna allow you to view the hexadecimal the stored in the system of this, sorry, in the file, so you can see the padding here. Hopefully this one convinces you that the padding is working fine, and we do have like let's say different way you can add, you can manipulate, you can work with the padding here. And I guess you're gonna work, design, and I think create different messages. Each of them have different size. Hopefully by doing this lab, hopefully you're gonna make sure that this whatever we cover in the symmetric encryption scheme, you can practice, you can understand, you can work with. Two things we're gonna add here. We talked about the initialization vector, okay? And generally speaking, the initialization vector has the following requirements. Supposed to be stored, let's say, or transmitted in plain text. So there is no need to, we said, doesn't need to be secret, okay? It shouldn't be repeated. Must be uniqueness or unique, and also it shouldn't be predictable. So when you talk about this one, maybe someone has said, I'm not convinced 100%. So in the lab, it's gonna do what? It's gonna try to test with why the IV or the initialization or initial vector supposed to be stored or transmitted in plain text. Why it should be repeat. This is the most important thing. Why it's unique. So we're gonna do the test. What if you perform the plain text or two different plain texts and encrypt use the same IV? Yeah, what's gonna happen? Or the same plain text, you encrypt with the same IV, or two different plain texts, you could use the same IV and see what the difference. You're gonna practice it. You have to do this one in the task 6.2, I guess. Yeah. Then after that, the other task you need to perform it. What if the IV is predictable? What's gonna happen? Show me why you said it must be not predictable. So you can see perform encryption, okay? So as a bad guy, you're gonna intercept the communication. You have some knowledge, and you know, for example, you have ciphertext for this one. You know the initialization vector for that used for in order to encrypt this say the ciphertext, and you know that, for example, the sender is gonna use a specific initialization vector for the next operation. So how can you use this knowledge in order to try to crack the system, in order to decide that ciphertext is going to be sent later? So that's one is going to play around here. We have two more things. One of them, watch part. I want from you to watch, two animation or two links in the YouTube, just to go over the this and the is in more details. Then at least, funny thing, at least summarize what we cover, and also using animation, it's gonna give you an idea what's going on. What's the encryption? What is the decryption? They start from the plain text, translate using ASCII to the number or the hexadecimal. Then after that, start to work with the operation. Anyway, that's all about the lab. Okay. Hopefully this is clear to you.